Great. Well, good morning, everyone. Thank you so much for joining us for this presentation, Hot or Not, Global Surface Temperature Measurements from Space. We're going to learn about the physics behind thermal remote sensing to measure the temperature of the Earth. Some applications will also be discussed. And this program is led by Dr. Nabin Malakar, Assistant Professor in the Department of Earth, Environment, and Physics at Worcester State University. Dr. Malakar has a wide-ranging research interest, including societal applications of remote sensing data, land surface temperature, air pollution, and application of machine learning to earth sciences. He previously worked in the NASA Jet Propulsion Laboratory and developed global land surface temperature and emissivity products for thermal infrared sensors onboard MODIS Terra, MODIS Aqua, Landsat, and VIIRS satellites. That's a mouthful, Nabin. I'm not even sure what I just read. So all 30 of us or so, let's give a big virtual round of applause to Nabin for joining us here this morning. And Nabin, you can take it away. Thanks so much.
Thank you so much, Robert. That's wonderful introduction. I've never heard about myself that much. Thank you. So hello, everybody. Welcome. It's my pleasure to be here, and thank you for organizing this. Your time is really valuable. I will get right into it. I am an assistant professor at Worcester State University, and I'm also serving as the Solar System Ambassador. My research topic is related to the remote sensing of the atmosphere and the surface, for example, to measure the surface temperature. And also, I also work on the air pollution issues. We can talk about those, in later time or during the question answer session. So the topic is hot or not, right? It's, how hot is it? The picture that I'm showing over here is one of the August months, the average for the globe. You can see the temperature, red is hot, and, the bluish purple is not, right? So basically, what I'm trying to emphasize in here is how simple physics principles can be used to measure the temperature. It's like developing a thermometer for measuring the fever of the earth. Like, for example, if you are down, cold, sick, and you have certain temperature, you wanted to use a thermometer, it should be well calibrated. And how do we do that from space? There is a lot of math involved, but I'm gonna introduce the basic ideas so that the math will not be the problem for us to understand what is going on. So if this is a picture of our world where you can see a lot of like a natural beauty in there, right? Except that the carrot is orange there. You think about this is a simple demonstration of our world. There is a sun, beautiful, shining, the birds flying around the trees, the others, the river there, the waves. But for a physicist, when you look at it, it looks like this, right? We don't all go crazy all the time, but you can literally figure out certain physics phenomena that's going around. This is a picture that I borrowed from Abstruse Goose, so thanks to them. You can see that there is a lot of processes that are governed by simple physics principles. It's either simple or impossible. So once you figure out, it's simple. Trust me on that. So you have all these processes going around, and you were trying to think of the physics process. And if you think about these processes, you can eventually win a Nobel Prize. As an example, last year we got a Nobel Prize in physics for 3 of the great scientists. The basic idea was that some of the calculations that you can do on the back of the envelope that is guided by physics can have a profound applications or implication for understanding the climate of the world, right? And because we just had a recent physics award on the Nobel Prize about quantum entanglement. I just wanted to bring up this issue that the climate science did win the Nobel Prize last year, and it was personal and awesome feeling for me too, because it's like every year we get different topic. Last year was for climate science. So the topic was understanding of the complex system. The complex system that looks like this can be understood by using some physics principles. And what do you use for understanding this? By using the data collection method is by looking at the Earth in a new light. If you're looking at a simple picture of the Earth as an example, Earth for a physicist, if you look at it, it's a rock, right? We rock. We go around the sun, right? It takes 1 year to go around, but the most of the energy, more than 99% of the Earth's energy is coming from the sun. And it's like a budget equation where you have the energy coming in, energy radiating out, and there is this energy balance equation that you can use a simple physics principle, which can literally dictate your calculations. And, the physics principles, when you first write it, is a really simple way of looking at the world. And it may not be accurate on that particular case because, if you calculate the temperature using this simple equation, it's coming out about minus 18 degrees centigrade, which is obviously not exactly right. And what we are missing in this picture would be the atmospheric constituent, right? The atmosphere serves as a nice blanket that goes around the, that's around the Earth, and that traps the heat radiation, and it warms the atmosphere in such a way that it makes the life possible. This is a picture that I borrowed from the JPL website where they were talking about the energy balance. So if you put the blanket around this cold Earth, right, instead of being at minus 18 degrees centigrade, now the atmosphere provides that greenhouse effect that keeps the temperature around 14 degrees centigrade. So this is literally a warm blanket that we have, right? For a physicist, when you look at it, right, the incoming radiation, outgoing radiation, the energy balance, you can literally divide this into a pie chart where there are different components that are playing vital role. And you can appreciate, we all can appreciate the fact that that energy balance is vital to sustaining the life as we know on the Earth. So this is a fancy picture. I will not go into the details about here, but you can see that there is a different dimensions, a different distribution of the energy that is going on. It's a really nice a semester-long course to talk about Earth's energy budget, where you can think about what happens when you change the constituent of the atmosphere, how the feedback provided by different gases, for example, can change the atmosphere, the warming effect of the atmosphere. And by exactly being able to do that using physics principle, Manabe primarily was awarded the Nobel Prize, right? It's basically the balance between the radiant energy that is reaching the Earth from the sun and the energy that flows from Earth back into space. That energy that is flowing back into space can be sensed by using some remote sensing observation platform. And I will talk about that in a minute, right? The energy that comes into the surface is in the form of the shortwave energy, short wavelength, right? And some of it is reflected by the atmosphere, some of it is reflected by the surface, some of that is used to heat the surface. And we will use basic physics principle to basically understand what is the distribution, how much can we sense, and can we use that observation to sense the temperature of the Earth. Now, in order to understand the impact of the energy balance over here in understanding the science of it, you will probably have to go deeper into its constituents, which is not the goal for us today. All right. We sense the Earth using different electromagnetic radiation, for example. And if I draw your attention to this graph, you can see that on the bottom shows the wavelength. Wavelength is like, for example, if you are thinking about waving your hand up and down, and then if you are moving along a line, wavelength is like one cycle of your oscillation that, you can go up and down and come back. So in one cycle, how far do you go can be depicted as the wavelength. All right. And the visible part of the spectrum that we are looking at is like a very small fraction of like 1 micrometer. Like, a human hair is about a couple of micrometer, like maybe 25 micrometer long. So it's like a really small fraction of that human hair that, is the electromagnetic spectrum that you can see through, right? The red color, the blue color, all that color that you can see is a really small part of the big range of that electromagnetic radiation that we are looking through. And we have the atmosphere that plays a critical role in the energy budget that we talked about. You can see that certain part of our atmosphere does interact with the atmosphere, right? That does interact with that electromagnetic radiation that is coming through. And this is the reason that, like, for example, because we have the opacity for our atmosphere is low on blue and green, right? And less on the red. This is the reason that our planet looks like a blue planet, right? From space, whenever you look back, you see a blue planet, and this is the reason, right? The opacity for red is less. Otherwise, if you have different opacity, you will probably observe different color of the planet. Thinking about the color, you can see that the Earth itself is a dynamic system where you can see literally the Earth breathing through the year. This is the yearly data, for example, looking at, if you're looking at the ocean, it's showing different primary productivity on the ocean, where the life system in the ocean is driven by some algae, the temperature, right? And on the land surface type, you can see the greenery and the ice covering is retreating and going back and forth, right? One year of the cycle basically shows different coverage of different land cover type. There is a consistent land cover, which is the Sahara region, that you can see is, almost all the time not moving, right? There is the southern belt where of the Sahara, where you can see the greenery moving in and out slightly, right? And there are certain regions, like, for example, if you look into the North American regions, you can tell when it is winter and when it is summer. Literally, it can breathe through. This is an example of a composite data of the Earth that we can compile from some of the NASA sensors. All right. Talking about NASA sensors, there are a lot of them that are observing the Earth. And these are called remote sensing platforms because you are literally sensing various parameters of the Earth from space without touching it. You can always touch, right? You can always have a sensor that's going to have like for example, if you're measuring the temperature, you can have a thermometer placed at different places. And those thermometers can give you the reading of different parts of the Earth. But imagine just putting thousands and thousands of thermometers around the surface. It just seems impossible, right? So we devise the instrument to go in this space and look down into the surface. And all we need to do this, and after that, we put the sensor on space, is that we now look down and then we try to figure out, okay, how much did the atmosphere contribute to certain part, and how much did the surface component contribute to the observation. It's like, imagine, being in a room and the room is filled with smoke, as an example. So if you're looking at a picture on the other side of the wall, right, let us suppose that the room is well lit, but the smoke that's present in the room can block your view in a way, right? You get some sense of what's on the picture, but because of, if the density of the smoke in the room is different, then you can probably figure out, if there is more smoke or less smoke, you can figure out how much smoke contribution is there for distorting your image that you can see through. So for us, we have to do the same thing, right? You're looking down into the atmosphere, through the atmosphere, and as you look through, you can figure out which component of the atmosphere is blocking your view, and put your sensor, where there is a little bit less interference. Usually, the physics guides this process. If you are trying to figure out the temperature of the Earth, as an example, you would probably have to put in a place where the absorption because of the atmosphere is less, right? You don't want to put your sensors, in the region where it's going to be like completely blocked, right? If your view is completely blocked because of the atmosphere, it doesn't provide you with the proper information. So you want to work with the place, like for example, this is around 10 micrometer that you can see here, where it provides a window of that opportunity for us to look into the surface. So you're literally using that atmospheric science to guide, right, to dictate where you are looking. All right. So this is the reason that we are looking at. That's about 10 micrometer, right? It's thermal infrared. That means that you are looking at the atmosphere at the wavelength, which is beyond your red color, which is beyond the color that you can see. You can design your sensor to get the radiation that is coming from the surface, and you can subtract off using some nice, math. You can subtract off this component, which is taking away certain component, right? So let us suppose that if there is, I'm trying to write. So if you know that the character of the atmosphere in this region, is taking away certain part of radiation, then you can figure out the math to solve the problem. So it's something like that. All right. Why is this important? If you can figure out the surface temperature and the other physical factor called emissivity, temperature is like how hot the Earth surface is, right? Emissivity is like how well a surface can emit the radiation, right? Like if you are thinking about people, some of the people are more vocal than the others, right? Some of the people can talk about their feelings more than the others, right? So those would be like higher emissivity. Similarly, if you're looking at the surface, for example, if the surface has higher emissivity, that means that surface can emit the radiation at higher strength than the others. An interesting thing about the surface is that, let me tell you that everything in nature is like a natural dancer, right? Everything that is above absolute zero, everything that is not frozen at low temperature is like, emitting some radiation, right? They are like a dancing, they are singing their song, whatever, you can imagine that as like your prescription of physics. They are emitting certain radiation, right? And by looking at that radiation, you can understand certain phenomena that can have societal application, right? One of the goals, for example, for NASA is to understand the Earth as interconnected system. And, a goal after that would be, once you understand this connection between different variables, different systems, can we use that for betterment of humanity, right? So we can understand certain properties, and then we can understand how that can impact the human well-being. As an example, urban heat island is one of the effects that you can feel in the urban area because of the built-up environment. Just imagine during the summer, if you are in a remote place where there is a lot of vegetation, that naturally feels cooler than being in a downtown where there is a lot of the cement, the built-up infrastructure trapping the heat and basically making the surface warmer than it is, right? So you can imagine it as a heat island where as you travel into those built-up environment, it has that built-up extra heat that you can sense. The impact of that is clearly visible now, clearly evident now, because apparently it can induce the heart diseases and other health impacts. Another important study that you can do is look into the evapotranspiration. Like if you are a farmer, you want to be able to tell whether your plant is going to make through certain day. Like as an example, if you are into gardening, you probably understand that when you see the leaves are turning yellow, it's already too late, right? It may be too late for it to recover. So if you can look into the signals that you cannot see, right? I told you about the thermal infrared signal that you can design a tool with, right? If you can sense that signal before your eyes can see it, before your sensor, the visible sensors can see it, you can literally tell which part of your field is stressed. So you can design your watering system, right? So the farmers would benefit from this a lot, because you can tell your plant is stressed before the plant is telling you in the visible ways, right? Before the leaves turn yellow, you can go and water it. Or sometimes it could be waterlogged system. There is a lot of water and the plant, is suffocating. The root system is suffocating, and that signal can also be basically sensed, right? Another application could be looking at the atmospheric profile, try to understand how the climate change can impact the atmosphere. The climate change can impact different surface of the earth, right? And that means that it will change the energy balance of a system. Once your energy balance is impacted, it affects the ecosystem, and ecosystem is the overall big picture that can influence the human well-being at the end, right? So you want to understand all of this. And one of my work is to look into the surface of the earth by using remote sensing. There are different ways of observing the earth, a couple of ways, and two of the famous ways are split window and the temperature emissivity separation. We use and then we can always talk about the details if you have questions on this, but a general overview would be something like a platform that you have from space. Like this is a MODIS sensor. MODIS stands for Moderate Resolution Imaging Spectroradiometer. It senses the earth. It has literally 36 channels. That's 36 set of eyes that look at the earth, and that is not only visible but also different wavelength. So you are looking at the earth not only in the red, green, blue, 7 colors of the rainbow, but you are also looking at it at different wavelength that's not visible to our eyes. By using those signals, you can tell a lot about how the earth is responding, how the health of the earth, literally. My instrument, or the instrument, not my instrument, the instrument that I work with looks at 1 kilometer resolution, meaning that each pixel is a kilometer. Like whenever you take a picture, you imagine a dot on your picture, right? That picture is 1 kilometer resolution. There are other sensors that use better resolution. For example, this is an example, but there are resolutions coming up better. If you use UAVs now, if you use higher resolution Landsat or other sensors, you can definitely get better resolution. But this is like as an example, proof of concept where you can understand certain system dynamics of the earth. So if you're looking at the earth, you're looking at the emissivity, and each of the surface, for example, has different characteristics of the emissivity. This is a diagram just basically showing the response of the different land cover type. For example, if you have dry grass, it has different emissivity at different wavelength than if you have sand. This is a quartz signal literally dancing around in different wavelength in different ways. They emit at different strength at different wavelength. And knowing that strength helps us to figure out what is the component that is literally putting out different energy that is coming in, right? So if you think of this like a circuit as an example, right? The incoming energy is distributed in different ways. And if you know the feedback from different parts, you can literally tell, how our system is responding and how we can use that. As an example, if you're looking at the emissivity of a quartz, like the sand, for example, and you are like literally trying to trace it in different wavelength, and you're looking at the radiation that you can sense at the top of the atmosphere, right? There are different, as I told you, there are different 36 channels, right? This is like a 3-channel, 29, 31, and 32 channels that you can see through. And you can see that at different wavelengths, different channels, they respond in different ways. And if you know the emissivity of the surface, then you can basically say which part is radiating how much, right? The distribution of that strength at which it is emitting. And once you figure that one, you can literally look at this window and talk about like, okay, the energy difference that is coming into your sensor can be divided at 31 and 32. That's why the split window name is there. And you just figure out the basic science of it, right? Like A plus B equals to C kind. And you figure out the sensor radiance. Voila, right? You can literally see how much is the temperature. If you can figure that one, that's cool, you know. So different land cover type, for example, you know, emit in different ways. NASA uses, you know, certain land cover types. For example, over here, a broad example of different land cover type like needle leaf, broadleaf, you know, for people in Oregon, for example, you know, different land cover type than for people in, you know, Midwest, for example, right? And for people who are living in Boston, for example, it could be some kind of, you know, concrete structure. So different land cover types have different emissivity. And once you figure that one out, it should be easy to do. But the problem is that if you look at a higher resolution picture, if you look at, you know, different constituent, all of them may not be well addressed if you are looking at mixture of different land cover types. And that can provide a huge problem for scientists if you're trying to understand how the system is behaving. As an example, if you have problem in assigning wrong, if you have problem because of wrong emissivity assignment, right? If you classified certain pixel in different ways, you can imagine that this leads to different temperature contribution, which means that your temperatures that you're reading through could get wrong. And that's where they, you know, if you are like trying to attack the temperature studies being wrong, then it's like, okay, well, your emissivity assignment is wrong. So therefore the temperature that you're reading through may not be right, right? And this is the very problem that we are trying to address. As an example, if you have the emissivity wrong for the Sahara region, as an example, right? The temperature difference can be huge, and that can lead to different sorts of problem. You know, if you're trying to understand the climate system, and if your temperature is more than 1 degree centigrade different, right? Then, you know, you're think about it. If you have a thermometer and you're trying to understand if you are hot or not, right? If you have a fever or not, and the difference, the error range of the thermometer is 5 degrees centigrade, right? 5 degrees centigrade can be life or death situation, right? So you want to be accurate. And we got a funding from NASA where we were trying to address this issue. And I will tell you that we got a lot of success in refining that algorithm, where we could tell that by going into this new algorithm, which is physics-based, we could tell that the emissivity assignment from the previous algorithm could have been wrong, and that could lead to the difference in the temperature. And if the temperature is different, then your thermometer is not working well. And as a science, we always try to refine our algorithm such that now, if you have better ways of measuring it, we go for it. So this is a new product that we have come up with, where we are now able to pin down the temperature within a degree, right? Within fraction of the degree. And how we do that is by using physics-based method that we talked about. Now, as you can see that the emissivity plays important role. So we basically have to go to different land cover types. This is Algodones dunes in the Southern California, where we went and then collected samples. You know, this is me and with my colleague in the desert, literally trying to collect the samples. And we bring that in the lab and we can scale it based upon the studies that we are doing, right? So we take the samples in, we find the emissivity characteristics, and once we have the emissivity characteristics, we can develop the algorithm in such a way that it gives us the better reading of the temperature. There is a paper based upon this study. I can talk details about it once, you know, if you have questions later. Now, this is a basic physics problem, and once you figure out that, then what you need to do is you need to figure out what is the atmospheric component, what is the atmospheric constituent. So it's like think of this like A plus B, you know, minus C, where you can, if you can figure out certain emission part from the surface, surface reflection part, atmospheric emission part, then you can literally go in, right? Use the black body radiation, which is thanks to Planck, about 100-year-old, 120-year-old formula, and you can figure out the temperature of the Earth. In order to do that, you need to, there is a little bit of details that we need to go in, like, look at the emissivity characteristics of different land cover type. Rocks emit in different ways than the soil, than the vegetation. And, once you figure that one out, you can correct your atmospheric contribution. You can literally derive what is the radiation that's coming from the surface. And once you figure that one out, you can find the radiation that is coming out, and that's what we are sensing. Once you have a better sense of the radiation that is coming from the surface, you can tell the better temperature, because once you can see that, once you subtract off the component of the atmosphere, it's like literally putting that sensor right on the surface of the Earth. Once you can figure that, you can figure out the temperature of the Earth. It's basic inversion by using the black body theorem, right? So this is what the basic recipe looks like, right? You are trying to look at the radiation, the energy that's coming from the surface, right? And then you are using the temperature and emissivity separation algorithm to derive the temperature, right? But, whenever you are about to cook something using the recipe, it looks simple in the beginning, but when you are implementing it, there are a lot of details that you have to take care of. So although the algorithm is simple enough for us to, go through, there is a little bit of detail that you need to implement. For example, there are different products that you have to get through, right? Like your data needs to be well geolocated. You need to have some sense of where is the snow, where is the ice, what is the atmospheric constituent, where is the cloud, because if you have the cloud, there may be the impact from the cloud that can impact your water vapor, for example, right? The calculation of water vapor. And whenever you are whenever your sensor is impacted from the water vapor, because water is also active component that can impact the atmospheric constituent in terms of the temperature, you want to remove those components, right? So once you do that, you get the temperature. So this temperature product, has been tested well in different land cover types. It's available globally. And you can see this is the month of August, for example, that is, globally available temperature product. You can see persistent cloud in the region there because of the monsoon. So because of the cloud cover, we could not get the temperature in this region. But, there are other sensors that that are working on to sense the temperature of the Earth. But if you have cloud, for our case, it doesn't work. You cannot sense the temperature for that. So you have to look for the cloud-free days, which is very good for certain other parts. So this is like a temperature and the emissivity that we can get at 1 kilometer resolution, and this product has been used to even look at this sensor, look at different sensor at higher resolution, and try to derive the science. For us, what's important is the science that you get out of it, right? So again, tying back to what we started with, the different applications. Once you have the temperature and the emissivity for different land cover types, you can understand how the system is behaving, how it is going around. And just to validate this, the temperature global product, we have looked at different land cover types, and we are literally trying to say that it works well in different land cover types. If you have sand site, like for example, Algodones, Great Sand, Skelso, all of these are sand sites, it works really well. Previous algorithms had a bias, greater than 1 degree centigrade, for example. Our algorithm, we used more than 10 years of data, and we found out that our new algorithm works a lot better in this case. And it is consistently working across in other land cover types too, like Lake Tahoe, Salton Sea, these are the water sites, grass site in Texas, Redwood in Washington, for example, they also work well. So we can claim that our algorithm is working a lot better. You can see the distribution of the temperature. If you are looking at the validation studies, you can see that the black one is our data set. It works pretty well compared to the older algorithm. So it's available for the public consumption. If you are looking for a field, you know, like if you are a farmer and it's like 1 kilometer, it may not be applicable for you, but you can use physics-based principle to study a different field site. For example, this is a Salton Sea area over here, and this is the Landsat emissivity. You know, we basically derive using the sensor data. You can see that if you are looking at your crop field, for example, right, in Kansas, we basically looked at a site, and you know, over here, for example, this is like irrigated corn, right? And if you're trying to see what is the emissivity of that, you know, you can look at the NDVI and then try to figure out how green the field is, and you know, you can adjust the emissivity based upon your radiance that you're looking at. And once you figure out that emissivity, you know, it's easy to invert, and you can see the field level temperature. This is an example over here. Like this is the border of US and Mexico. This is the algodonos dunes where we took our sand emissivity, sand samples from. And these are the fields that you can literally see the temperature. You know, a certain area may be well irrigated than the others. So you can say whether the surface is hot or not, right? That is like one application that you can see at the field level for if you're a farmer. If you're trying to study climate, you can also see whether certain land cover type is disturbed and whether it is recovering well or not. We did this small study where we are looking at the Los Angeles region, and you know, we're trying to see whether it is applicable for understanding the impact on the human health. As an example, we looked at like a about that's like 11 years of data, like a decade of data as an example, and you can divide that data into whether it is you know, warming up or not. So if you divide that data into different sites, for example, what you can see is that so first 6 year would be, for example, you know, the blue one, and then the later 6 year would be the red one. You can see that because of the drought or other impacts in the region in the Los Angeles, certain areas are warming up, right? Like, you know, shifting to the right than the others. Again, this is not a conclusive proof that of the climate change, because it's a short-term data, okay? But you can definitely use these kind of studies to tell whether certain parts are warming up more than the others. As you can see, I have divided this data set into 9 different regions, right? And you can imagine that, like, for example, you know, the ocean side would be well regulated because of the presence of the water than the inland areas. And if you look at the trend of the warming for different regions, you can tell that certain regions are warming you know, at rapid rate than the other. Like, you know, this is like a terabyte of data that I processed by looking at different regions, like 9 regions for 12 different months. You can basically look at the trend of how they are warming up and cooling down. You can see certain regions are cooling, certain regions are warming. The cooling could be, again, this is a short-term data. The cooling could be because of certain you know, it could be La Nina effect, could be short-term effect, which needs more investigation, could be precipitation in short-term, right? Because if you have precipitation in certain time, then it can cool the surface. But if you look at certain land cover type, you can see that certain areas are warming more rapidly than the others. And you can see that is obviously the effect of the wildfire that you get in the Los Angeles area. Like this is 2003, where you can see the land cover change, right? So this is certain, you can see the yellow regions, which is different land cover. And in 2014, we had big fire and cleared a big part of the land. And obviously that you can see as the signature of warming in certain regions. Luckily, this is not the region where people live, but imagine all of the wildlife that could be living there could be impacted by the wildfire, the warming. If you use that data set to look at the warming in different regions, you can see that certain regions are warming than the others, especially the region in the downtown Los Angeles area, for example. You would be concerned about, like, okay, if there are people living there, and then your area is either warming up significantly in last 10-12 years and the others, then you probably want to have some closer look at the regions. Specifically, if we found out that if there are certain regions that are warming up because of the urban heat island effect, then you want to be concerned about that. Because if you are, if you have a lot of people living in a region that is warming up and that have the health implications, specifically during the heat wave events, right? People can be admitted to the hospital. You want to have a better policy of like probably creating more cooling center or some other policy level decision that you need to take. Especially, we found out that certain regions which are cooling up could be demographically impacted, because there could be the region where people with on average $30,000 yearly income, for example, living in there. So these are people of certain demographic that are living in the area that are being impacted by the change in the climate, by the atmosphere, the heat wave, for example, that are impacted. And you want to literally take care of your constituent, right? So you can distribute your resources based upon these science results. Definitely, you can see the impact of the climate change. If you look at the long-term impact, and you can use different sensor fusions over here to see that certain areas are warmer, like for example, than the others. You can tell which area is more affluent than the others by also looking at this temperature data set, for example. The downtown, for example, if you look at the aggregate income, household income, you can literally tell which area has greenery, which area has more income than the others. It's not accident that we can see the heat island impacting certain demographic than the other areas. It can be political too fast. So this is a study that is done by my colleague, where they looked at different warming and cooling and the temperature impact during different times of the day. And you can use these science data sets to derive policies, again, to let's say have a cooling center, or think about, can we do something about the people being impacted during the hot days. Some of these are published as the science documents. If you are interested, please feel free to contact me. These are published peer-reviewed documents, papers that's out there. You can look into the details of that. But the long story short is that people say that everything is either physics or stamp collecting, but I'm trying to do a physics as well as stamp collecting, right? Have fun meanwhile. Basically, thermal infrared sensors are useful in understanding the dynamics of the Earth in the wavelength that you cannot see, that you can design a sensor that you can look at the Earth and you can derive the temperature. And that can have some policy level impact. If you have a consistent level data set that you have for 30 years, you can even see the impact of the climate. These sensors have been on the space for since 2002, for example. So we have 20 years of data. So if we can have 30 years of data set, then we can definitely tell whether there is impact of the climate. So in 10 years, we can talk again using different data sensors, whether it has the impact on the climate. There has been impact on the climate because of the human footprint. So this is a brief overview of the thermal infrared and how it can be used to understand different dynamics, different surface temperature. Every year we get the news about the heat island impact, the heat waves, impacting different parts of the globe. And that seems to be the recurring theme for the upcoming, next next century, right? So can we use our resources to better understand the impact on the human? That would be a proper question to ask. Does the warming in the place impact us, right? Like, does it impact more where people are living, or does it impact more where the people are not living, like a third pole, for example? If it impacts the region that are in the polar regions, that's gonna lead to melting of the ice. What will be the implication of warming in those regions? So we need to think about it. Now, the last part, I'm gonna basically, draw your attention to certain, let's say, application of this. Like, for example, if you have the data set like this, can you use that data set for societal well-being? So that would be the next question that I would be interested in. With that, I'm going to stop it here. If you have questions, please feel free to put it in the chat.
Yeah. So Nabin, wonderful job as expected. And as Nabin said, if anyone has any comments or questions for him, please put them into the chat now, and we'll take a few minutes if we have any. We'll give it a good 60 seconds, Nabin.
All right.
And so Nabin, what are you teaching at Worcester State?
So I teach physics and environmental science. And this semester I'm teaching energy. So basically some of the things that I talk about is looks complicated in the beginning, but I convince my students that some of these are like a back of the envelope calculations. Like, we are literally calculating how much does it cost for you to boil a cup of coffee, right? So using that principle, we can literally say, okay, if we are cooling certain part of like your area, how much does it cost in terms of the dollar cost? If you are using certain resources, what is the impact on the climate? So you can do some back of the envelope calculations to come up with some number which makes sense. So that's some of the things that I do.
Great. Well, Nabin, you've left them speechless. So I think we'll wrap up here. But Nabin, you threw a lot of information at us in just about 45 minutes. So that was wonderful. And I wish you the best of luck with all your future research. I think you're doing an important work over there. So Nabin, do you have any last words for the audience before we wrap it up?
Sure. So thank you so much for your attendance. I appreciate your time, and thank you, Robert, for having me here. There is a lot of information there. Obviously, you can Google me, find me, and ask me questions. I will be more than happy if you have questions. If you wanted to get in touch and get some more information, I'll be more than happy. Thank you.
Great. Thank you, Nabin. And so folks, for the folks still with us, next month on Wednesday, November 2nd, we're having a presentation at 11 o'clock, just like today, inside look at International Space Station's Bishop Airlock. And we actually, the guest speaker, we're going to have two guest speakers, but one of them is the man who actually designed it. So we're going to have the designer of the International Space Station's Bishop Airlock with us on Wednesday, November 2nd at 11 o'clock. So really looking forward to that one. So, but Nabin, thank you so much for your presentation this morning. Folks, look for that email tomorrow with the recording and the feedback survey. And I hope to see many of you next month on November 2nd. So thanks again and have a great day. Thanks, Nabin. Bye-bye.